So today I'm tackling the mighty subject of whether maths can save the whales and cure cancer. And these are two examples of the use of mathematical modelling, which is going to be the main topic of the lecture. But I wanted to start with one of my favourite quotes of all time, and I hope you'll forgive me for this quote, but it's from Douglas Adams, and here it is. On the planet Earth, man had always assumed that he was more intelligent than dolphins because he had achieved so much. The wheel, New York, wars and so on, whilst all the dolphins had ever done was muck around in the water having a good time. But conversely, the dolphins had always believed they were far more intelligent than man for exactly the same reasons. Okay, so today we're going to have a sort of whale-type theme, but also look at some of the achievements that we can do, some of the things that we can do by using mathematics. So we'll start, given it's 2020 and we want to kind of look forward, with some of the big challenges that we as human beings face in the 21st century. And I'm sure if I was to ask anyone to give their top 10 challenges, somewhere on that list would be curing cancer, and somewhere else on the list would be saving the environment, either climate change or, in this case, saving the whales. And both of these huge challenges are things that mathematics can help in the solution of. I won't say maths can solve them, but maths can be part of the process of solving these. And I'm going to use cancer and saving the whales as two big examples of the way mathematics can be applied to the real world. But you're probably thinking, what's that got to do with maths? Isn't maths an abstract production of the human mind? And if you thought that, you'd be absolutely right. Maths on its own isn't designed to solve practical problems. Maths is meant to be an abstract subject. You have axioms for maths, such as axioms of geometry or arithmetic, and then you follow through those axioms to see where you get to, and that usually means that you have some sort of rigorous argument that leads to what we call mathematical theorems, and perhaps the most famous of these theorems is Pythagoras' theorem. And these are sort of eternal truths. They're things that are always true and will be true forevermore. So that's what mathematics is. On its own, it doesn't have anything to do with real life. Although later on in this lecture, we will see how Pythagoras' theorem can be used to save the whales. So why do I say maths can be used in these sort of useful ways? Well, as a mathematician, and this is actually my day job, this is what I do at the University of Bath, I work a great deal with people from other disciplines, such as scientists, engineers, biologists, economists, and whatever. And we work together to turn real-life problems into mathematics. And then we try to use all the abstract maths that I described in the last slide to solve these real-life problems. And this process of taking a real-life problem, turning it into maths, solving it, and then trying to understand the answer is what is called mathematical modelling, and that is my day job. So today I'm going to tell you about what I actually do. And mathematical modelling is the subject of this talk, and we're going to use whales and cancer to illustrate its power. So you're all familiar with at least one example of a mathematical model. So since the kind of beginning of the 20th century, mathematics has been used to forecast the weather. And the way we forecast the weather is we start with the laws of physics. So with the weather, that is the way the air flows, how things heat up, how moisture evaporates, and so on. And then we encode these as what we call differential equations, partial differential equations in particular. We then take lots and lots of data, which typically comes from satellites, and that data tells us what the weather is doing today. And then if we know what today is, and we can solve the equations, then if you use a large enough computer, then you can actually forecast tomorrow's weather. And despite rumours to the contrary, this is actually quite a successful process. It doesn't always work because weather is complicated, but actually forecasts of the weather using mathematical ideas are pretty accurate. And you have to continually update these forecasts by feeding in more and more data. And it is also very important that the results are presented in a way which someone who is not a mathematician or a scientist can understand, and that's where the weather presenters on the TV come in. So that is a mathematical model. And all models are to a certain extent like this. And here is the, quotes, official version of mathematical modeling, in the sense that if you type mathematical modeling into Wikipedia, this is what it does. It produces this diagram for you, which is kind of right. And the idea is you start with reality, whatever that might be, the weather in this case. And in one case, you look through actually what happens in real life. So you might perform experiments, or with the weather, you actually look at what's going on. On the other sense, you make a model, which is formulating these equations, which allows you either to do simulations with a computer or to do some sort of mathematics coming down here. And then hopefully everything agrees at the bottom. And then you say, I've done a good job. I can simulate and predict into the future. And this is the way weather forecasting works. And this process to get this right for the weather has taken hundreds of years to try to understand how all the models work and how the mathematics works. So that's the official Wikipedia view. As I said, this is my day job, and this is my view. It's rather less organized than that. It's rather like doing a crossword. You stare at the thing for ages and you can't do anything, and then you finally spot one thing you can do, and you put that in, and that gives you a clue. So this is kind of, you try to identify what's going on by comparing to data. You go around this kind of loop of equations, you compare with the data all the time. So instead of this kind of systematic flow, there's a constant comparison between what you think is going on and what you actually observe. And then at the end of the day, you get to know what's going on. And if you think that looks like some sort of art rather than a science, you'd be basically right. Okay. So that is the process of mathematical modeling. You start with reality, you turn it into maths, you compare the maths with reality constantly, and eventually you get some equations which hopefully tell you a bit about what's going on in the real world. So, as I said, this is going on all the time in weather forecasts, and a weather forecast is what we call a simulation. Now, a simulation is where you have an attempt to get everything as right as you possibly can, so tomorrow's weather really is what the computer says it's going to be. And in a simulation, you would typically have a supercomputer running code with billions of lines. And these things take a long time to run. They're very, very hard to get right, but you kind of get them right over many, many years and take a lot of investment and resource. And simulations are used to model factories. Here's a nice logo of a factory going on. They're also used in 2013, I was a consultant from the London Underground, building simulators for how the London Underground would operate, and that allowed us to kind of understand how people would move in and out and how everything could be organized in case there was an emergency or so on. So that is a simulation. But that's not really what I want to talk about today. I want to talk about something else, which is a mathematical model. And what a model is where you take everything that's going on, but instead of trying to put it all into a computer and getting something which takes a very long time to run, you try to boil it down to its essence. You try to think, what are the key equations which are really telling us what's going on? Ideally, equations that you can then analyze using mathematical tools, and then once you do that, you can then predict into the future with mathematical formulae rather than having to run a supercomputer every time. And Einstein, who produced an entire model of the universe in one equation, now called the Einstein field equation, came up with a lovely quote, a model should be as simple as possible and no simpler. And he's absolutely right, and the tricky bit is working out how simple something should be to be actually useful. And that's kind of what I'm going to explore a bit in this lecture. So that's what a model is, a simplified version of reality which we can calculate with and hopefully tells us something about reality itself. Now, the idea of mathematical modeling, in a sense, goes back to Newton. And Newton wrote down the laws of mechanics and the law of gravitation, and he used these to construct a model of the solar system. In his model, he treated the planets not as planets with lots of things going on, but as simply points, which is already an approximation, and he just considered a fairly small system, but that system allowed him to make predictions about the way the solar system would behave, which have proved incredibly helpful in understanding the way the universe works. So this was basically the first model. And one of the things about models is that by finding mathematical relationships, you can essentially understand what happens as you change things without having to do millions of computations all the time. And a really, really good example of this is that if you write down Newton's equations for the solar system, you find that there's a relationship between how far a planet is from the sun and the time it takes to orbit the sun. Basically, the time it takes to orbit the sun squared is proportional to the distance from the sun cubed. And what that means is that if you find a new planet, and we're finding planets all the time now with advanced telescopes or asteroids in the solar system, once you know how far it is away from the sun, you can calculate its orbital period from a very straightforward formula. And that's an amazing result. It encapsulates a lot of physics into one simple result. So that was a prediction that Newton made from his model. Now, the idea of using mathematics to model the universe is really quite revolutionary. I think it's one of the great discoveries of the human mind. Of course, I'm biased in that. But Newton proposed it, and it wasn't kind of very respectable until a big event that happened in the 18th and then the 19th century. And the first thing that happened was the discovery of the planet Uranus. Now, the 13th of March is a very important day in astronomy because it was on the 13th of March in 1787 that William Herschel, who, by the way, lived in Bath, where I am based, looked up at the heavens and discovered a new planet. And that was the planet Uranus. And when they looked at the planet Uranus and they plotted its orbit, they found that it obeyed Newton's model almost. Basically, it did what it should do, but there was a slight difference between what it was predicted to do and what it actually did. And at that stage, they were confident enough in Newton's calculations to think, well, if it's not doing what Newton says, there must be a reason for that. And they looked at the orbit of Uranus, and they looked at how different it was from the prediction that Newton's model said it should be. And they deduced that the reason it wasn't keeping quite to its orbit was due to the influence of something else. And they postulated there was another planet out there influencing it. And two mathematicians, John Couch Adams in Cambridge and Leverrier in Paris, separately calculated where that planet should be. And Leverrier asked a German astronomer to point his telescope in the right direction, and that astronomer did, and they found the new planet. Adams also asked the Cambridge astronomers to do it, but they were too interested in having a good dinner at the time, and so missed the opportunity. So the Germans got there first, but the point about this was that they found a new planet purely from the results of the predictions of a mathematical model. And this was one of the first occasions ever where something completely new and completely unexpected had been found as a result of a piece of mathematics. And that was a major breakthrough. Finding Neptune was less important than realizing that by using mathematics you could discover new things about the universe. And that kind of made mathematical modeling respectable. And not long after the discovery of Neptune, Maxwell wrote down equations for radio waves, and they predicted radio waves, and many, many other predictions have come from mathematical models. So it's a very, very powerful technique. So nowadays, mathematical modeling is very widely used. If you go over a bridge, that bridge will have been designed using a mathematical model. If you look for the Higgs boson at CERN in the Hadron Super Collider, all of those calculations will be done using a mathematical model. Chemists use mathematical models to find the properties of new compounds. In biology, mathematical models are used to predict the spread of disease, and we'll look later on in this talk about the use of such models in cancer. Somewhat less reliably, mathematical models are used in economics. Anything involving human beings is tricky, and sociologists use mathematical models to look at crowds or cities. And I put psychohistory because if you read Isaac Asimov, you'll see how mathematical models were used to predict the future of the entire galaxy, although I'm not quite sure of the maths involved there. So this is how a lot of science is now done through mathematical modeling. Mathematical models are also used by irresponsible newspaper journalists. I'm not infrequently rung up by them. I was rung up just before Christmas and asked by a journalist what was the mathematical model for the perfect way to pack a fridge at Christmas. And also another journalist asked me for the mathematical equation of the best Christmas tree. I'm not sure if you recognize this, but that is apparently the formula for the perfect joke. I'm not quite sure what all the bits are, but P is puns. So the more puns you have, the worse the joke. Okay. Amusing, but not very scientific. Here's a rather more useful model. Last year, I gave a talk about the mathematics behind climate change, and we tried to understand the way climate changes by running simulations, and they're quite difficult to use, but we can simplify those simulations down to a certain number of key influences. And one of the ways to predict the temperature of the Earth is to look at a balance between the energy which comes to the Earth from the sun and the energy that's radiated from the Earth back into space. And if we let T be the average temperature of the Earth, S be the radiation from the sun on average, A is the reflectivity of the Earth, and E is the absorbability, the emissivity of the atmosphere. That's how much gets out through the atmosphere. And balance them, then you get this lovely model which relates the temperature to the radiation of the sun, the reflectivity of the Earth, sigma is a constant, and the absorption of the atmosphere. And this model here, which is really simple, it's just a simple formula, is actually very powerful. It allows us to make predictions of how the Earth's temperature will change as the amount of carbon dioxide in the atmosphere changes. And this is one reason I think I am personally confident that the climate is changing, because this model here essentially predicts that. So that's a model for climate. I won't go through the derivation of this, but if you are interested, go back to last year's lecture on the maths of climate change, and you can have a look and see where that model comes from. But I thought I would kind of work you through, in this lecture, a simple example of how the modeling process works before I get onto the more complicated examples of whale saving and cancer, by answering the basic question of how did the mathematician cross the road? Now, I hope you're all very well-behaved people and only cross the road at pedestrian crossings. So here we have a pedestrian crossing, and here are cars. And in the UK, at least, the way a pedestrian crossing tends to work is you walk up, you find the lights, you press a button, and then you wait for a certain amount of time, and after a certain amount of time, the lights change, and you get the green person flashing, and you can cross. And it's always been a question to me of why do we have a delay when you press the light? The reason you have a delay is that if you don't have it, and you have lots of pedestrians crossing, then the lights are basically always red if you're a car, and you can never get across. So you have a delay so that enough pedestrians can accumulate at the crossing to make it worthwhile for everyone to cross without delaying the cars unduly. So using a mathematical model, can we estimate what the optimal delay is? So I'm going to take you through the process of how we try to answer that question, and then, as with all mathematical models, we will investigate whether the answer we get seems reasonable or not. Okay, so this is a real-life question. So with all mathematical models, you have to start with thinking about what is the problem you're trying to solve and what sort of assumptions do you make. And one reasonable assumption is that pedestrians kind of arrive at a fairly steady rate at the crossing, and similarly, traffic arrives at a fairly steady rate at the crossing. Secondly, if you have a bunch of pedestrians, then when the green person starts flashing, they can all cross the road, and it takes them a certain amount of time to cross the road. And the final assumption I'm going to make, which is kind of the most controversial of these, is the best delay, the optimal delay you want to put on the lights, is one which maximizes the total amount of pedestrians that cross the road and the total amount of cars that cross the crossing. Okay, so if you allow lots of pedestrians to go through but no cars, that's not so good. If you allow lots of cars to go through and not so many pedestrians, that's not so good. But if you allow the maximum amount of both cars and pedestrians, that seems a reasonable thing to design. Okay, so those are our 4 assumptions. That is what I would call the physics of the problem. Now we have to turn that into mathematics. So what do we mean by pedestrians arriving at a steady rate? It means that in any time t, the number of pedestrians that arrive is a times t. So for example, if you say 1 pedestrian arrives every minute, then in 10 minutes you get 10 pedestrians. Similarly, in the same time, you'd say that b cars arrive, and one would generally assume that more cars arrive than pedestrians, so you might get 10 cars in a minute, so in 10 minutes you get 100 cars. Okay, so that's the sort of mathematics behind our first 2 assumptions. The next thing is that when the lights are green, we'll assume all the pedestrians cross, and none of them are naughty pedestrians and cross when they're red. And let's suppose the lights go red, then because it takes the number of pedestrians that arrive in a time t is a times t, you wait for a time 1 divided by a for 1 pedestrian to arrive. That pedestrian then presses the button. You then have a delay d, and after that time d, the lights go red, and that pedestrian will cross, and also all the other pedestrians that have arrived in that time will cross as well. So that's our kind of little bit of mathematics. Now let's build on that mathematics. And this is kind of the main mathsy bit here. The total time that the lights operate is going to be the time it takes for our first pedestrian to arrive, which is 1 divided by a, plus the delay, plus the time to cross. So that's the entire time in what I call a cycle between the red light and the green light. In that time, this is the number of pedestrians that arrive. It's the one that arrives and press the button plus the delay time times a. And in the same time, the number of cars that cross this is the time it takes for the lights to change completely, and that's the number of cars. And so what we call the flux, which is the average rate of cars and pedestrians getting through the junction in this time, is this rather fearsome formula here. Okay. So that's the math. Now the next stage of the modelling process is to try to take a formula and interpret it in terms of what we actually want to know. So what you want to do with this formula is say, well, how does the flux of cars and pedestrians change as we change the delay in the pedestrian crossing light? So what we can do is plot this thing here as a function of d. And to do that, I've taken some reasonable choices. I'll say, well, let's suppose 10 cars arrive per pedestrian, and the time of t of crossing is, let's say, 10 seconds, or whatever, doesn't really matter. And then you can plot this as a function of the delay. And if you plot it, here's the delay here in seconds. Here is the amount of cars and pedestrians on average that go through. And when I did this, I found it was a slightly surprising result. And the result was that the longer the delay, the more pedestrians and cars you could get through. And basically what this means is that the pedestrian presses the button, lots and lots of pedestrians arrive at the crossing, and after you've waited for a very long time, it goes green and you can all cross, and lots of cars go through whilst that's happening. So the conclusion from this model, with that assumption, is you make your delay as long as possible. Okay. It's interesting that in Bath, the delay is much shorter than it is in Edinburgh. And that's a conclusion from the model. But of course, what the model has left out is one extra assumption, which is that after a while, people get fed up and going to cross anyway. So you basically make this as large as possible until your pedestrians give up, run out of patience. But I was kind of surprised by this, and a model should surprise you. It should give you an answer which you don't expect. And I like this example a lot, because then you can go off and typically when I talk to other people about this, you then have a huge debate, because after a while you get to this with people crossing when they shouldn't do. Is this model, how can we improve it? And one way to improve on the model is to put in an extra assumption, which is that it's not just the flux that you want to optimize, but you want to optimize the kind of patience of the pedestrians. So you put in something else which makes things worse if you wait too long. And that's where you start building in human factors, and that's where everything gets interesting. So I'll let you go off and think about that and think how you might improve on that model and see what you come up with. So that's how a model works, starting with basic assumptions, doing the math, seeing what it presents, seeing whether you agree with it, and then going back and revisiting your assumptions. And this is essentially how the process works. Now, mathematical modeling is very, very powerful, but it very much has its limitations and drawbacks. And I want to kind of tell you about some of these. And a lovely quote from George Box, who constructed economic models and wrote a very seminal paper about this in 1976, is that all models are wrong, but some of them are useful. Now, what I think he means by this is that all models are wrong because they're approximations, but even a bad approximation is better than nothing at all. So that's what he was getting at here. So here are some pitfalls. So pitfall number one is don't eat the menu. What that means is when you construct a mathematical model of reality, it is a model of reality, it isn't truth. So when you listen to climate scientists say the Earth is going to be 3 degrees hotter in 100 years' time, that's a little bit naughty. What they should say is that according to mathematical models of climate change, that we predict that the world will be 3 degrees hotter in 100 years' time. All models have limitations, all have approximations, and I think it's very important when you use maths to simulate the real world, which I do, you also tell people what the uncertainty is in that. So it's much more reasonable to say a climate model predicts with certain uncertainty that we'll be 3 degrees hotter in 100 years' time. So don't believe your models completely. Secondly, this is one of my favorites, is don't be what I call a mathematical drunkard. So the story behind this is a drunkard is looking for some money, and a policeman comes up and says, "What are you doing?" And the drunkard says, "I'm looking for my money." The policeman says, "Where did you drop it?" He said, "Well, I dropped it all the way down the street." And the policeman says, "Well, why are you looking for it here?" And he says, "Because the light's better." And what a mathematical drunkard does, and sadly we all do this, I'm as guilty as anyone, is that we try to take a real problem and turn it into a problem that we can solve, and then solve that and think we've achieved something, which is a bit naughty. We all do it. But you have to be very careful when you do mathematics on reality to make sure that you are dealing with the real problem and not one that you've kind of adjusted to something you can yourself do. Third one is, again, we're all guilty of this, what I call the ivory tower syndrome. Academics are terribly bad at this. We think we're so clever and wonderful, and all our students tell us that we're clever, well, sometimes they do, that we can just sit in our universities and wait for the world to come to us, and that will be good enough. And that isn't true at all. In order to do effective mathematical work on the real world, you have to get your hands very, very dirty. And this is a lovely quote from Synge, who was writing way back in 1944, where he was part of a team developing mathematical models to basically, this is all essentially to do with the bomb, building the atomic bomb at the time, offering the wisdom that if you sit in your office and wait for the world to come to you, it's not going to come to you. You've got to get your hands dirty. And in a minute, I'll tell you how you can get your hands dirty. And the final pitfall is the curse of the formula. This is the newspaper that rings me up and asks me for instant formulae. Generally, it isn't like that. With the climate model, we were lucky to be able to boil it down to a formula which works. But normally, when you do mathematical modeling, you can't do everything just mathematically. You have to use some sort of computer or some approximate method. And as I say, newspapers love formula. And this formula here, I was once asked to comment on, which is the formula for the perfect kiss. Again, I'm not quite sure what the terms mean, but I say don't forget to keep your brackets on when you do it. Before I get onto the whales, I just want to say a little bit about how we teach modelling. Modelling is such an important subject that it's really important it is taught well. To a certain extent, it's taught at schools now with the new A-level syllabus. To a certain extent, it's taught at universities. But the only effective way to teach the process of understanding the world through mathematical ideas is to get your hands dirty, as I just alluded. And one of the most powerful ways of doing this is what we call the study group model. And this is an idea which started in the UK about 50 years ago and is now used worldwide, where we get teams, typically of students, and we get them to work for a whole week on problems which industry poses, and with the idea of trying to solve the problem and presenting the results in 1 week. And if you think that maths is something you just do in isolation and is done very theoretically without any contact with the real world, that's not how modern modelling is taught. We now teach it very much as collaborative teamwork and with real problems with real industrialists. And this is an example of one of our study group sessions going on. This one was in Ireland. In Bath, we've got one of these workshops in a couple of weeks when we're going to be looking at 3 problems, one of which is how well you can plant trees, and another was to do with traffic flow. Right, well, that's kind of set the scene with mathematical modelling, and now I want to get on to kind of the real business of the lecture by showing how with mathematical modelling we can save the whales and do something about curing cancer. And we'll kick off with how maths can save the whales. Now, I want to warn you in advance here that I want to show you how the modelling process works in reality. And what that means is that there is going to be some heavy-duty maths coming up. So I thought I'd warn you on that so you can brace yourself when we get to it. It doesn't matter too much if you don't follow all the details, but I want to kind of show you kind of the way we go about doing things in reality. So this is a project I'm actually actively involved with, and I collaborate with an organisation called SAISH, who's very much involved in the process of saving the whales. So, until fairly recently, whales were hunted. They were nearly hunted to extinction for certain species. Fortunately, some years ago, there were treaties that were put into place which stopped the hunting of whales, more or less. There's still one or two countries that hunt a few when they really shouldn't. But unfortunately, even though whales are no longer being hunted, there are still significant threats to them. The biggest threat of all is climate change, and that's difficult to sort out. Another big threat is pollution. Another threat is overfishing. But what I want to talk about today is the threat that's posed to whales by ships. So ships obviously sail around the ocean, and although whales are big, ships are a lot bigger, and not infrequently ships strike whales. And that's generally the ship wins and the whale comes second. And that is quite a significant threat to whales, is the threat of ship strikes, and the related threat that if you have a ship which is, say, doing some sort of prospecting for oil, and they let off an explosion to prospect for oil, that can injure a whale that is near the ship. And the bottom line of this is that if you want to save the whales from ship strikes or other interactions with ships, you want to make sure that whales are a good distance away from the ship. So the generally accepted wisdom is that the nearest you want a whale to a ship for the whale to be safe is about 400 meters. Okay, you might want to be further away for bigger ships, but 400 meters is what's generally considered the nearest you want a whale to get to a ship in order for it to be safe. So I will call 400 meters here the danger zone, where the whale is under threat, and further away, the safe zone. So you're on a ship, you don't want to collide with a whale, you want to make sure you're at least 400 meters away from the whale. The basic question then you have to ask yourself is, where are the whales, and how do I know where they are so that they can be safe and the ship won't collide with them? And that's the question we're going to have a look at using mathematical modeling. And that's how we're going to try and save the whales. And this is a very real thing that we are actually doing. So we need to work out how far away whales are. And there are various techniques for doing it. If the whale is on the surface, you may just be able to spot it with radar, but that's not very reliable. If the whale is under the surface, you can certainly detect it with sonar. So sonar is where you send sound out from the ship, it bounces off things and comes back. It was what was used in the Second World War to find submarines, what's still used to find submarines. However, it's a terrible thing to use to find whales, because if you send sonar out from a boat and it hits the whale, it has the rather unfortunate effect of knocking out the whale's own sonar, and then the whale gets disorientated and gets lost, and can actually die as a result. So you really do not want to use sonar. In fact, one of the biggest threats to whales is the use of sonar on ships. The third method, very straightforward, is you look for them, and that can be effective if the whale is on the surface or just under the surface. And a kind of nice job is to be the official whale spotter on a ship. However, it's not reliable particularly. But the final way you can work out how far a whale is, which doesn't hurt the whale at all, is to listen. It's what's called passive sonar. Passive sonar, which is often used to find submarines as well, is where you simply listen to what's going on. And whales make sounds. A whale sings, that would make a sound, and in principle, by hearing that sound, we know there's a whale somewhere in the neighborhood, This is a spectrograph of a whale sound. And the question is, where is the whale? So I want you to imagine there might be a whale over there somewhere. Unfortunately, in the rush to come today, I forgot to bring my whale with me. But anyway, imagine there's a whale there, and the whale makes a sound. Then you can hear that sound on the ship. And if you listen for the whale, this is what a typical sound looks like. That's time going along here. U is the intensity of the sound. And what you hear is not one sound, but lots of sounds. You hear sounds in pairs, and this is due to reflections from the sea surface. And then you get something, and you get something here. This is what you hear. And the reason you get this sort of pattern is here's your whale, there's your ship, and you get one sound which travels a distance L, which is the distance from the whale to the ship, and you get another sound which is reflected off the seabed and arrives a bit later and a bit lower in intensity because it's gone further. And you can actually get another one which reflects off there and there and there, and that's why you get that. That's what we call the direct sound, that's what we call the echo, that's what we call the second echo. So that's what you hear. You hear these things. This is a stylized picture. I'll show you a real picture in a minute. So you can measure the time of arrival of the sounds and also the difference in time between the first sound and the echo. And what I want to show you is how, with a bit of mathematical modeling, you can actually go from that observation to work out where the whale is. Okay, so this is the task that we have. Right, the next slide is super mathsy scary, so apologize, but anyway, here we go. Yes, this is my job. What sound are pressure waves in water. That's what they are, is pressure waves in water. And as I said, when you do a mathematical model, you start with the laws of physics. And we know what the law of physics is for pressure waves in water. There it is. This is called the wave equation. And funnily enough, we're going to meet this later when we look at how you cure cancer. The same equation. That's called the wave equation. And U here is the intensity of the sound. C is the speed of the sound. T is time. And this funny thing here describes how the sound changes as you move in space. That's already complicated. So when you construct a model, you have to start making simplifications. The first simplification you make is that you assume that the sound has what we call a single frequency. And that means that the sound looks like that mathematically. And if you substitute this into here, it becomes this slightly simpler equation here, where omega is the frequency of the sound. This doesn't mean anything. Again, when you talk about reality, you always have to think about what's actually going on. You have to think about the scale at which you're doing things. And a typical length scale in whale spotting would be something like the distance you need to be away from the whale to be safe, which is round about, well, it's 400 meters, so I'll divide that by 2 so that we're halfway. And if you do that and you rescale, you get this equation here. Okay, that already looks a bit scary, but with a bit of maths, you can do something rather clever. This is the actual equation that sound travels on under the sea, and the company that I was working with this, and then I said, well, actually, you can simplify this a lot. And the reason you can simplify this is you have a number here, k, which you can work out. It's the length scale times the frequency divided by the speed. And we know, with some extra maths, that if that number k is large enough, then sound doesn't go like a wave, it travels like a straight line. We all know that light goes in straight lines, but in our experience, sound tends not to. But if you've got large enough distances and speeds are just about right, sound can also travel in straight lines. So we took this formula, plugged in the actual frequency. A whale sings at about 30 hertz. The speed of sound in water is 1,500 meters per second. And if you work out this number here, you get 25. And that's quite large enough. Anything bigger than 10 is good enough. And you get this wonderful simplification, which is that if you're looking at whales and distances consistent with whales and the frequency consistent with whales, then the sound from the whale travels to a very good approximation in a straight line. And that simple observation meant that huge computer codes, which were not getting very far and taking ages to run and were very uninsightful, could be replaced by a single mathematical idea which meant you could do calculations on the back of an envelope which could tell you where the whales were. So I'm going to show you that calculation. It's not actually very hard. So we'll go back to this problem here. Here's our whale. There's the ship. It's a distance L from the ship, or you can have an echo which goes down to the seabed and comes up like this. And I drew these as straight lines because they are straight lines. We've worked this out, that the sound goes from the whale to the ship in a straight line or bounces off the seabed in a straight line. So the first sound goes a distance L in a time t1 at a speed c, and it takes that time to arrive. And if I knew what t1 was and knew what c was, I could work out what L is. Unfortunately, we don't know when the whale makes the sound, so we don't really know when that is. But there's my first time here. And then we have an echo, which comes a bit later. And we're going to work out how long the echo takes using a bit of mathematics. When I introduced the idea of mathematical theorems, I said the oldest theorem around is Pythagoras' theorem. There's Pythagoras' theorem, which says that if you have a triangle, A, B, and C, with a right angle, then we get this amazing formula, A squared plus B squared equals C squared. That formula was discovered by the Chinese about 3,000 years before Christ, 5,000 years ago, well before Pythagoras. Okay. But Pythagoras got his name attached to it. In case you can't remember that, there's a little poem which goes like this. A right-angled triangle opined, my hypotenuse squared is refined, for if anyone cares, it's the sum of the squares of my other two sides when combined. So if you remember nothing else in the lecture, remember that. Okay. How do we use this wonderful theorem? The way you use it is there's the whale singing to the ship. That's the direct path. This is the echo. Let's work out how far the echo takes. It takes a distance s to get to the sea and s to come back. The depth of the sea is h. And using Pythagoras' theorem, I can work out that. Good old Pythagoras. And we do this twice, so we get that as the distance that the echo takes. The time it takes is that divided by the speed of sound. And therefore, the difference between hearing the first sound direct from the whale and the echo is this. By the way, this is the hardest maths in the talk. So this is what I measure. This is what I want to know. And in order to find out how far the whale is, I have to solve this equation, which hopefully any good A-level student can do. If there's some good A-level students in the audience, I hope you can do this. And if you do that, you get this formula. I know I said you shouldn't get formulae, but this is an honest formula. It's not the formula for a kiss. This is actually derived with some physics. And what this formula does here says that if I know what the depth of the sea is, which is h, speed of sound is I know, and I measure this, that tells me how far the whale is. And here we have it in pictures. And this is what we actually use for real whale saving, is we measure this, we know what this is, and this allows us to find L as a function of this. And basically it says if there's a long separation between hearing the whale the first time and hearing the echo, then the whale is actually quite close to you and is in danger. And if there's a short separation, then it's far away from you and is safe. And it even tells you 30 milliseconds in this case is the effective difference between safe and danger. And I'm really pleased with this. This is how a bit of mathematical modelling leads us to a formula, and that formula is then something you can build into a piece of apparatus which allows you to work out where the whales are and therefore be far enough away from them and therefore to save them. So maths really does save the whales. I should say this, as with all things, this is a bit of an approximation. One thing is that we generally don't know what the depth is, and you find the depth by looking at other echoes. And secondly, if you make real measurements, they look like this, rather than the nice pointy things which I said earlier. And you can see you've got other effects coming in. But this is the next stage in the modelling process where you build in extra accuracy in order to make the thing a bit more precise. So there we are. Math saves the whales. On to my next big claim. Can maths help to cure cancer? So I have here a picture that I took at a conference I attended last year. Every 4 years, all the applied mathematicians in the world sort of get together for one big conference. And the public lecture, the big lecture of the conference, was Maths and Cancer. And here's the slide the person giving the talk put up from a lady called Susan Fitzpatrick, who's the president of one of the chief cancer charities. Despite billions of dollars and some of the world's best brains being hard at work, cancer has not been beaten. Different approaches complementing classical ones are required. One of them may be to increase the use of tools offered by applied mathematics. And then she said, and I'm really happy about this, mathematicians have a unique set of skills that may be very useful, even essential in the war on cancer. Now, this is a vast subject, and I've only got 8 more minutes to cover a vast subject. So I'm going to talk a little bit about generalities and then go back to show how whale saving can cure cancer. So what is cancer? And cancer is a nasty disease where you get uncontrolled cell growth, giving you a tumour. And if the tumour grows uncontrollably, it will kill the patient. And that's difficult, and obviously doctors and many other scientists have worked very hard for many, many years to understand the processes behind how tumours grow, and also how drugs and other techniques can be used to reduce the size of tumours. Where does maths come in? Well, maths comes in a number of ways. One is you can use mathematical equations to help to predict how tumours grow. So there are teams of mathematicians all around the world that build mathematical models of tumour growth, and these are used by doctors to help understand how the tumours will grow inside the body. You can use other mathematical models to look at how drugs can get into the body, get absorbed by the tumour, and therefore restrict the growth of the tumour, and also why tumours can become resistant to the use of these drugs. So mathematical modelling is used in all of these areas. In the transcript for this talk, I go into a bit more detail if you want to read, and you can see how these models work. But this is a vast subject, and I can't possibly cover very much of it today. And just to give you a flavour, this is a model here for how tumours grow in the initial stages before they get attached to the blood supply and things get really serious. So this is the sort of work that's going on all around the world, where one of the aspects of mathematical modelling can be that it suggests experiments that clinicians can then do, and to, allow them to better forecast how tumours will grow and how the chemicals work. Unfortunately, I don't know much about this, but I do want to now just finish the lecture with telling you about something I do know, a project that I've been working on quite recently, which is a little bit like whale saving, but how we use some of the ideas in whale saving to cure cancer, which might sound bonkers. But one of the things about mathematics is that very different problems physically can actually lead to the same mathematics, and therefore the tools that you use to solve one problem can then be taken over to save another problem. So what I want to do to finish this talk is tell you how we can destroy tumours by using sound. Now, I said you shouldn't look for whales using sonar, because sonar is fairly high-intensity sound that's used to detect things and can damage the whale. And that's a bad thing. But if you can use sound to destroy a tumour, then that's a good thing. And there's a technique called the HIFU technique, that's called high-intensity focused ultrasound, where you take ultrasound, that's the same thing that's used when you're looking for a pregnant lady, you'd use ultrasound to see how the baby is growing. If you take high-intensity ultrasound, but somehow can focus it, then at the point of focus, you have a chance of being able to destroy a tumour. And this is called the high-intensity focused ultrasound methods, where you have a transducer sending sound waves to attack a tumour. And this is guided using magnetic resonance, that's this big thing here, to show you where the focal point is, giving you what's called the magnetic resonance high-intensity focused ultrasound method. And here's a cartoon of it. There's the transducer, there's the tumour, there's the focused ultrasound. Where's maths in this? Well, everywhere. So mathematical modelling is used firstly to work out the intensity and timing of the burst from the transducer. It's used to design the transducer so you get focus here, and is used to help image the results so you can interpret what's going on. What's the math? Well, we've seen how sound can be studied for the whales. If you take the same equation, this famous equation that I put up earlier, and work out the same value of k, with ultrasound, the frequency is much higher, but the length scales are much smaller. And if you put it all in, you end up with that value of 20.9. For the whales, it was 25, and that means it's the same problem. 20 and 25 are close enough to mean that exactly the same maths can be used. And in other words, sound at that intensity and frequency travels in straight lines. And so we use straight line models to work out where the sound's going, to work out its intensity. That's this number Q. Here's the formula, wonderful formula, which tells you what the temperature of the tumour is as a function of this. This is how we can use that to work out the intensity and the time. And the bottom line is, it more or less works. As with all medical processes, it takes a very long amount of time of testing. I was introduced to this problem in one of these study groups that I mentioned earlier, but this process is being used in the Sick Kids Hospital, which is in Toronto, and it has been successful in destroying bone tumours without cutting people open. So it's in kind of process, this development, but the point is, here's how a bit of mathematical modelling, identical to the saving the whales maths, can actually be used to cure cancer in this case. So just to conclude, the potential applications of mathematical model are almost limitless. Watch this space, there's so many more things you can do. But as I said earlier, don't believe everything you say, and always be aware of the limitations of any piece of mathematics when applied to the real world. Thank you very much.